You probably imagine sending Bitcoin like sending an email, a digital coin flying from your wallet to someone else's. That's completely wrong. Nothing moves. Bitcoins don't even exist as discrete objects. When you hit send, the mechanism is entirely different from what most people picture. The data format behind every transaction hides one of Bitcoin's most elegant engineering tricks, a design that protects money people won't spend for years. To understand it, we need to rethink what Bitcoins even are. Think about how land ownership works. When Alice sells a parcel of land to Bob, no physical land moves between them. Alice goes to the land registry, a government office, and files paperwork that convinces the registry to update its records. The entry changes from owner, Alice, to owner, Bob. The land stays exactly where it always was. What changed is a record in a database. Compare this with physical cash. When Alice hands Bob a dollar bill, an object physically moves from one person to another, and that's direct transfer. Land ownership doesn't work that way. It works through database updates. This distinction matters because Bitcoin works like land, not like cash. When Alice sends Bitcoin to Bob, no digital object travels between wallets. Alice creates a transaction, a small piece of data, and broadcasts it to the Bitcoin network. The network consists of full nodes, computers running software that independently validates every Bitcoin transaction and block. Each full node checks the transaction against its rules. If valid, every node updates its own copy of the ownership database. The entry changes from "these coins are spendable by Alice" to "these coins are spendable by Bob." The coins are entries in a distributed database, not objects. Sending Bitcoin is useful shorthand, but the mechanism is persuasion, not transfer. A transaction is the data that triggers this database update. When serialized, converted into a sequence of bytes for storage or transmission, it follows a specific format. First, 4 bytes for the version number. This tells nodes which rules apply to this transaction. Next, in the modern format, come 2 special bytes, a marker byte and a flag byte. We'll return to these. They contain a clever trick. Then comes a variable length integer for the input count, followed by the inputs themselves. Inputs reference previous transaction outputs that the sender is authorized to spend. This is where Alice proves she owns the coins. After inputs, the output count and the outputs. Each output specifies an amount and the conditions for spending it. This is where Bob's ownership gets defined. In the modern format, witness data follows the outputs. The witness holds signature and proof data, separated from the main transaction body under the segregated witness upgrade, segwit for short. Finally, 4 bytes for locktime, which can restrict when the transaction becomes valid. That version field at the very start isn't just a label. It solves one of Bitcoin's hardest engineering problems. A pre-signed transaction is one that has been signed but not yet broadcast. It's held for future use. The Lightning Network depends on these. 2 parties open a payment channel and create pre-signed transactions that can be broadcast months or years later. Sometimes the signing keys get discarded after signing. Consider the consensus upgrade, BIP68. A BIP is a Bitcoin improvement proposal, a formal design document proposing changes to Bitcoin. BIP68 adds new constraints to the sequence field inside each transaction input. If BIP68 applied to all existing transactions, those pre-signed transactions sitting in Lightning channels could suddenly violate the new rules. They become invalid, the funds will be permanently destroyed, and nobody holds the keys to sign a replacement. The solution? BIP68's new sequence constraints apply only to transactions with version 2 or higher. Version 1 transactions, including all those pre-signed Lightning channel transactions, remain completely unaffected. The old rules still govern them. No funds are lost. When developers created those pre-signed transactions, they used version 1 because version 2 was reserved for future rule changes. Version numbers aren't metadata, they're a safety mechanism. Each version creates a protected zone where existing transactions can't be broken by future upgrades. Version numbers protect against rule changes, but the serialization format itself had to evolve, and the trick they used is elegant. When Bitcoin added the segwit, transactions needed to include witness data, but legacy nodes, older software, still had to function. In the legacy format, the byte right after the version number is the input count, how many inputs the transaction has. A transaction with 0 inputs is always invalid. It makes no sense. The segwit format places a 0 byte in that exact position. Legacy nodes read it as 0 inputs, reject the transaction as invalid, and move on. No crash, no confusion. Modern nodes see that 0 and recognize it as a marker signaling the extended format, and they read the next byte, the flag currently set to hex 01, then pass witness data after the outputs. 1 byte, 2 interpretations. Legacy nodes reject gracefully. Modern nodes pass correctly. The flag byte's other possible values are reserved for future format extensions. Both of these design choices, versioning and the marker byte, reflect a single philosophy: upgrade without breaking the past. Bitcoin holds real money. People lock funds in contracts that won't execute for years. Every protocol change must guarantee that existing transactions remain valid. Version numbers create isolated rule domains. The marker byte enables format evolution through deliberate incompatibility, using invalidity itself as a signal. Reserved values like unused version numbers and flag byte values beyond 1 provide room for changes that haven't been invented yet. This philosophy continues today. Version 3 transactions have been proposed for relay policy changes, rules individual nodes use to decide which unconfirmed transactions to forward. Version 3 would add anti-denial of service constraints without affecting version 1 or 2 transactions at all. If you build protocols using pre-signed transactions, the practical rule is clear: never use features reserved for future upgrades. Bitcoin Core's test mempool accept RPC can verify your transactions comply with current rules. Bitcoin's transaction format isn't clever bypacking. It's a contract with the future, promising that money locked up today won't be destroyed by tomorrow's improvements.